Welcome to CSC 201, Lesson 3.3, Statements with Multiple Quantifiers. When a statement contains more than one kind of quantifier, we imagine the actions suggested by the quantifiers as being performed in the order in which the quantifiers occur. So consider a statement of the form, for all x in set D, there exists a y in set E such that x and y satisfy some property, p of x, y. So in this instance, you should imagine that someone else is to pick whatever element in D they wish. So you're going to let somebody pick a random element in set D. And then you get to go search in set E for a y that matches, that works for that particular property and that particular x. So that is, each x in D may pair with a different y in E to satisfy the property. So you let somebody pick a random x in D, you get to find any y in E that satisfies the property. So for example, if I said, for all non-zero real numbers R, or for every non-zero real number R, there exists a real number S such that R times S equals 1. This states that every non-zero real number R has a reciprocal S. So you get to imagine that someone chooses a non-zero real number R. So for every non-zero real number R, someone gets to pick a random one, and then you hunt through the real numbers and find an S. You find an S that exists that is its reciprocal. i.e., someone chooses R equals 2/3 and you find its reciprocal S equals 3/2. And you could do this no matter what somebody chose as the first value. All right, this is in contrast with a statement of the form, there exists an x in set D such that for all y's in set E, so I've reversed the quantifiers. It was for all x, now it's there exists. It was there exists, now it's for all. So I reversed the order of the quantifiers. There exists an x in set D such that for all y in set E, x and y satisfy the property. It looks similar, but the order is reversed. So here you imagine that someone is looking for one particular x in D that will work no matter what y in E anyone might choose. So here we're looking for one particular x that works with every y. For example, if I said there exists a real number R such that for every real number S, R times S equals 0. This states that there exists a single real number R, one particular number, so that when you multiply it by every real number, you get 0. Okay. Paired with any other real number, you get 0. And this is a true statement. There is a real number R, so that when you pair it with every real number S, R times S is 0. And that real number R is R equals 0, right? If you multiply 0 times every real number, the product is 0. All right, a college cafeteria line has 4 stations: salads, main courses, desserts, and beverages. The salad station offers a choice of green salad or fruit salad. The main course is spaghetti or fish, and the dessert has pie or cake, and the beverage station is milk, soda, or coffee. So we have 3 students that go through the line and make the following choices. So Uda, Tim, and Ewan, they each choose a dinner, and I have it on the next page, a picture of what they choose. Okay, so we're going to use this information, this picture, to write each of the following statements informally and find its truth value. So I have, there exists an item L, so I'm looking for one particular item, such that for every student S, S chose L. So I'm looking for one item that when paired with every student, S chose it. So if I write this informally, I would say there is an item that every student chose. Okay, let's see. Is that true? So I'm looking for an item that has 3 lines going to it because every student would have chosen it. Spaghetti has 2, Uda and Tim. Fish has 2. Oh, pie. Pie has 3 lines. Uda, Tim, and Ewan all chose pie. So this is true. Pie is the item that every student chose. Okay, next one. There exists a student S. So we're looking for one particular student such that for every item L, S chose L. So we're looking for one particular student that chose every item. So there is a student who chose every item. And if I go and look at the picture, let's see. Uda did not. She didn't take fruit salad. Tim did not take a green salad. So he took a lot of things, but not a green salad. And Ewan did not take a salad at all. So this is false. There is no student that took every item. Okay. C, there exists a student. So I'm looking for one particular student such that for every station Z, there exists an item L and Z such that S chose L. So there is one student such that for every station Z, there exists an item L and Z such that S chose L. So let's just look at the second half here. There exists an item L in Z for all stations. For all stations, there exists an item L in Z such that S chose L. Okay, so we're looking for one particular student, and then the rest says that for every station, there is an item in that station such that the one particular student chose it. So this says that there is a student who took an item from every station. And let's see if that's true. See, Uda took an item from every station. So did Tim. Ewan did not, but Uda and Tim did, so this is true. We only needed one for it to be true. Okay, finally, there exists, for all students S, for each student S, and for each station Z, for every student S and for every station Z, there exists an item L in Z such that S chose L. So for all students and for all stations, there is an item at each station such that S chose it. So this says that each student took an item from every station. Right? So for all or for every student, so each student, every station, each student, each station, item at the station that the student chose. So each student took an item from each station. And this is false. No student took an item. There is one student who did not, right? So let's go back and look before we declare it false. Each student took an item for every station. Okay, so Uda took an item from every station. But we're not looking for there exists a student. We're looking for all students took an item from every station. So Tim took an item from every station, but Ewan did not. Ewan did not take a salad. So this is false because we found a student, we found a counterexample. False. Counterexample, Ewan. Most problems are stated in informal language, but solving them often requires translating them into more formal terms so that we can use the rules that we know, like the negation rules, for example. The reciprocal of a real number A is a real number B such that AB equals 1. The following two statements are true. Rewrite them formally using quantifiers and variables. Every non-zero real number has a reciprocal. So every is a hint that this is a universal. So we would say for every non-zero real number A, there exists a reciprocal. So there exists a B in the reals. There exists a non-zero real number such that AB equals 1. And then B, there is a real number with no reciprocal. If I wanted to state that more formally, it's not true, but we can still state it formally. There is a real number with no reciprocal. We would say there exists an X in the reals such that for all Y's in the reals, X times Y is not 1. So it says that we can find a real number X such that if we search all the reals, we cannot find a reciprocal. You can use the same rules to negate statements with several quantifiers that you used to negate simpler quantified statements. So you already know all the rules, it's just applying them in more complicated ways. So if we want to negate for all x in D, there exists a y in E such that P of xy. Well, a for every statement becomes an existential. So we would say there exists an x in D such that not this. So just to apply the rule, I would say there exists an x in D such that not the rest of the statement. So the rest of the statement is there exists a y in E such that P of xy. And then I can use my how to negate this statement. So this is an existential, it's going to become a universal. I have a there exists, it's going to become a for every. So I'm going to copy the beginning part. I have a there exists an x in D such that, and then negating this part is going to become a for all y in E, P of not this, right? So negating the existential, this becomes for every, and then not this part. So I have for all y in E, not P of xy. And you could do it all in one step. You can just think about it as distributing this not. So as you distribute this for all x in D becomes the existential. And then this existential, there exists a y in E, becomes a for every. And then the not P of x. So as you distribute, the for every becomes a there exists. The there exists becomes a for every. And then not P of x. And then we can do the same thing for this one down here. I'll write it all out for this time. So not there exists an x in D such that for all y in E, P of xy. Well, there exists an x in D is going to become a for every x in D. Not the rest of the sentence. For all y in E, P of x, y. And then I'm going to work on negating this second piece of the sentence. So I copy the first piece, for all x in D. Now, not for all y in E, that becomes there exists a y in E such that not P of x, y. We finish up with an example using Tarski's world. Your textbook talks about this a lot. So it's just a square with different colored shapes on it that are labeled with letters, and Tarski's world just discusses the relationship between the different shapes and colors. Okay, so we're going to define each of these predicates. Triangle x means x is a triangle. Circle x means x is a circle. Square x, x is a square. And then I have blue, gray, and black x. Those just define the color. And then we have right of xy means x is to the right of y. Above xy means x is above y. And same color as xy means x has the same color as y. And then we have some domains to define. T will be the set of all triangles, C circles, S squares, and D is the set of all objects in Tarski's world. So we're going to use formal logic notation to write each of the following sentences and write a formal negation for each statement. Decide which is true, the original or the negation. For every circle x, x is above f. So first we're just going to write it formally and then we'll decide whether or not it's true. For every circle x, so I would say for all x in C, x is above f. So we would use the predicate above, and x is above f. So like that. Now f is a particular object in the picture. So let's look at the picture. So we're saying for all circles C, for all circles, so let's just like all the circles, there they are. Okay, all those circles x, are they all above f? So that is true. All the circles are above f. Okay, so we can mark that as true. And then we also need to negate it. Okay, so the negation would say there exists an x in the circles such that f is above x. So above fx. And this is false. There is no circle where f is above it. All right, part B. There is a square x such that x is black. So to write it formally, I would say there exists a square x, there exists an x in the set of all squares such that x is black, so that would be black x. That's the predicate, x is black. And that's true. There is a square that is black, E. To negate it, the there exists becomes a for every, for all x's in the set of squares, not black x. Okay, so this says for all x's in the set of squares, not black. So all x's are not black. And that's false because we do have a black one. All right, C says that for every circle x, so let's just go ahead and start translating. For all x's in the set of circles, there is a square y, so there exists a y in the set of squares such that X and Y have the same color. So the predicate was same color as X, Y. So let's see if we can decide whether or not this is true. For every circle, there is a square such that they have the same color. So I have to check every single circle. So for B, that's gray. There is a gray square. And then C and A, those are both blue, and there is a blue square to match it. So for every circle, there is a square that has the same color as it. So this is true. And then the negation will be false because negations always have opposite truth values. But to negate it, the for all x's becomes a there exists an x in C, such that the there exists a y in S becomes a for all y in S, not same color as XY. So this says there exists a circle such that for all squares, they are not the same color. And that is false because it has to have the opposite truth value. Okay, D says there is a square X such that for every triangle Y, X is to the right of Y. So there is a square that's there exists an X in the set of squares such that for every triangle, so for all Y's in T, X is to the right of Y. So the predicate for to the right of is right of, and X is to the right of Y. All right, so I need to go back up and look at the picture to decide if this is true or not. Okay, so there is a square X such that for every triangle Y, X is to the right of Y. So I'm looking for one single square that every triangle Y, X will be to the right of it. So here I have two squares here that G and J. Those can be my X's. So I could say G works, right? So that for every triangle, G is to the right of the triangle. Or the same thing is true about J. So this is true. There is a square such that for every triangle, the square is to the right of the triangle. So true. And then the formal negation would be for every square, for every X in the squares, there exists a Y in the triangles such that not right of X, comma, Y. Okay, so this says that for all squares, there is a triangle such that the square is not to the right of the triangle. Or you could reverse the order here. You could say, for all X's in the squares, there exists a Y in the triangles, such that instead of writing not right of XY, we could write right of YX. And that is false.